In 1969, a human boot pressed into lunar dust for the first time in the history of our species. And then, for more than half a century, we simply stopped going back. Here is the unsettling truth about why the most technologically advanced civilization ever to exist on this planet cannot seem to repeat what it accomplished with computers less powerful than a modern pocket calculator. The year was 1969. The mission was Apollo 11, and 2 American astronauts descended to the surface of the moon in a fragile craft held together by rivets and hope. That moment represented the single greatest exploratory achievement of humankind. An event watched by an estimated 600 million people on television sets around the world. An event that proved beyond any reasonable doubt that the human will, when properly funded and politically motivated, could overcome obstacles that only a decade earlier had seemed like the fantasies of science fiction writers. Neil Armstrong stepped off the ladder of the lunar module Eagle, planted his boot in the fine gray regolith of the Sea of Tranquility, and uttered words that have been repeated so many times since that they have almost lost their staggering meaning. One small step for a man, one giant leap for mankind. But what happened after that giant leap is, in many ways, far more interesting and far more troubling than the leap itself. After Apollo 17 returned to Earth in December 1972, carrying astronaut Gene Cernan, the last human being to walk on the lunar surface, no person has traveled beyond low Earth orbit. Not one. For over 50 years. The astronauts and cosmonauts of every spacefaring nation have been confined to a thin shell of space a few hundred miles above the planet's surface, living and working aboard space stations like the International Space Station, which orbits at an altitude of roughly 250 miles. The moon, by contrast, sits approximately 238,000 miles away. The distance between where humans routinely operate in space and where they last venture beyond is staggering. And the question that naturally follows is one that millions of people have asked in classrooms, on internet forums, in casual conversation, and in serious scientific debate. If we could go to the moon in 1969, why haven't we gone back? Some people assume the answer is simple, that we lost interest or ran out of money. And while there is a kernel of truth in both of those assumptions, the full story is vastly more complicated, more fascinating, and in some respects more alarming than most people realize. There are those who take the question in a different direction entirely, arguing that we never went to the moon at all, that the Apollo missions were an elaborate hoax staged in a television studio somewhere in the Nevada desert to fool the Soviet Union and the American public. That conspiracy theory, which has persisted for decades and gained new life in the age of social media, will be addressed directly in this account, because it is impossible to have an honest conversation about why we haven't returned to the moon without confronting the false premise that we never left in the first place. But the purpose of this exploration is not to dwell on conspiracy theories. The purpose is to lay out, in clear and honest terms, the scientific, engineering, financial, and political realities that have kept human boots off the lunar surface for more than 5 decades, and to examine whether the current generation of space programs and private enterprises can finally break through those barriers and return humanity to its nearest celestial neighbor. The story begins, as it must, with the Apollo program itself, because understanding what Apollo actually was, both its miraculous achievements and its terrifying limitations, is essential to understanding why repeating it has proven so extraordinarily difficult. The Apollo program did not emerge from a pure scientific desire to explore the moon. It was born out of fear, competition, and Cold War politics. In the late 1950s, the Soviet Union stunned the world by launching Sputnik, the first artificial satellite, into orbit around the Earth. And then in 1961, Soviet cosmonaut Yuri Gagarin became the first human being to travel into space. The United States, which had considered itself the undisputed leader in science and technology, was suddenly playing catch-up in what the press called the space race. President John F. Kennedy, recognizing that American prestige was on the line, stood before a joint session of Congress on May 25, 1961, and made one of the most audacious promises in the history of government. He declared that the United States should commit itself to achieving the goal, before the decade was out, of landing a man on the moon and returning him safely to Earth. It was not a scientific goal, so much as a political one. Kennedy understood that whoever controlled the high ground of space will hold an enormous psychological and strategic advantage in the global struggle between democracy and communism, and he was willing to spend almost any amount of money to make sure that advantage belonged to America. And the amount of money that was spent was, by any historical standard, almost incomprehensible over the life of the Apollo program. From its inception in the early 1960s to its conclusion in 1973, the United States government poured approximately $25 billion into NASA, an amount that in today's dollars translates to roughly $150 billion or more. At the peak of Apollo spending, around 1965 and 1966, NASA's budget consumed approximately 4.5% of the entire federal budget, a share that dwarfs the fraction allocated to the space agency today. To put that in perspective, NASA's current budget sits at around $24 billion, which represents roughly 0.35% of federal spending, about 1/10 of what was during the Apollo years as a proportion of the national budget. The sheer scale of the financial commitment that made Apollo possible is almost impossible to overstate. At its height, the program employed more than 400,000 people across NASA, its contractors and its subcontractors, spread across facilities in Texas, Florida, Alabama, California, and dozens of other states. Entire industries were created or transformed to serve the needs of the program. The aerospace sector in the United States was reshaped in ways that persist to this day, and all of that money and manpower was directed toward a single, clearly defined objective: beat the Soviets to the moon. The clarity of that objective was one of Apollo's greatest strengths, but it also contained within it the seeds of the program's eventual cancellation, because once the objective was achieved, the political rationale for continuing to spend such enormous sums evaporated almost overnight. The technical achievement of Apollo was genuinely miraculous, but it is important to understand just how close to the edge of disaster every mission actually was. The program's first major tragedy struck before any crew ever left the ground. On January 27, 1967, during a routine launch rehearsal test for what was then called Apollo 1, a fire broke out inside the command module on the launch pad at Cape Kennedy. The cabin was filled with pure oxygen at slightly above atmospheric pressure, and when a spark, probably from faulty wiring, ignited the atmosphere, the three astronauts inside, Gus Grissom, Ed White, and Roger Chaffee, were killed within seconds. The disaster led to a complete redesign of the command module, including a new hatch that could be opened quickly from the inside, changes to the wiring insulation, and a switch from a pure oxygen atmosphere to a nitrogen-oxygen mix at launch. The fire delayed the program by nearly 2 years, but it also forced NASA to take safety far more seriously than it had before, and the redesigned spacecraft that emerged from that process was significantly more reliable than the one that had killed those 3 men. When Apollo 11 finally launched on July 16, 1969, atop the colossal Saturn V rocket, it carried the hopes and anxieties of an entire nation. The Saturn V remains, to this day, one of the most impressive machines ever built by human hands. It stood 363 feet tall, taller than the Statue of Liberty, and generated 7.5 million pounds of thrust at liftoff, enough to shake buildings miles away and to be heard as a deep, bone-rattling roar by the million or so spectators who had gathered along the Florida coast to watch. The rocket performed flawlessly, sending the Apollo 11 spacecraft on its 3-day journey to the moon. But when the lunar module Eagle began its descent to the surface, things started to go wrong in ways that could have ended the mission in catastrophe. As Armstrong and Buzz Aldrin guided the Eagle toward its planned landing site in the Sea of Tranquility, They noticed through the window that the computer was steering them toward a field of boulders, any one of which could have destroyed the fragile lander on contact. Armstrong took manual control and flew the Eagle laterally, searching for a clear spot, while the fuel gauge ticked steadily downward. Mission Control in Houston called out the fuel warnings with increasing urgency. 60 seconds of fuel remaining, then 30 seconds. Armstrong found a clear patch of ground and set the Eagle down with an estimated 15 seconds of fuel left in the descent stage tanks. 15 seconds. If the landing had taken even a few moments longer, the engine would have run dry, and the lunar module would have dropped the remaining distance to the surface in a crash that would almost certainly have been fatal. Buzz Aldrin later recalled that the tension in the cabin during those final moments was almost unbearable, and that when the contact light finally came on and they heard the call out from Houston confirming that they were on the surface, the relief was overwhelming. That is how close Apollo 11 came to becoming Apollo's greatest tragedy instead of its greatest. Triumph. The story of Apollo 13 is even more harrowing. Launched in April 1970, Apollo 13 was intended to be the third manned lunar landing. But approximately 56 hours into the mission, an oxygen tank in the service module exploded, crippling the spacecraft and leaving the three-man crew, Jim Lovell, Jack Swigert, and Fred Hayes, stranded in a damaged vehicle 200,000 miles from home. The explosion knocked out both oxygen tanks, the fuel cells that provided electrical power, and most of the command module's life support systems. The crew survived only by moving into the lunar module Aquarius, which had been designed to support 2 men for 2 days on the lunar surface, and using it as a lifeboat for 3 men over 4 days during the long, cold, terrifying journey back to Earth. The ingenuity of the mission controllers and engineers on the ground, who improvised solutions to problems that had never been anticipated, is one of the most celebrated stories in the history of space exploration, but it is also a stark reminder of how dangerously thin the margins were on every Apollo mission. Even the missions that went relatively smoothly were riddled with minor anomalies, computer alarms, communications glitches, and moments of genuine peril. Apollo 11's computer threw multiple program alarms during the descent, designated 1202 and 1201 errors, which indicated that the onboard computer was being overwhelmed with data and was shedding lower priority tasks to keep up. The alarms nearly caused Mission Control to abort the landing, and it was only because a quick-thinking engineer recognized the error codes as non-critical that the mission was allowed to continue. Apollo 12 was struck by lightning twice during launch, which temporarily knocked out the telemetry and navigation systems. Apollo 14's lunar module had a faulty abort switch that had to be bypassed with software, workaround just minutes before the descent engine fired. Apollo 15's parachute partially failed during splashdown, resulting in a harder-than-normal water landing. Every single Apollo mission that reached the moon carried with it the possibility of disaster, and every single one that returned safely did so in part because of extraordinary luck. The astronauts themselves have been remarkably candid about this. They knew the risks and they accepted them because the political and personal stakes were so high that caution was considered almost a luxury. That willingness to accept extreme risk is something that has fundamentally changed in the intervening decades, and it is one of the key reasons why returning to the moon has taken so long. The Apollo program ended not with a triumphant final flourish, but with a quiet cancellation driven by shifting political priorities and public apathy. The original plan called for missions through Apollo 20, but after the successful moon landing defused the urgency of the space race. Funding was slashed and missions 18 through 20 were scrapped. Apollo 17, which launched in December 1972, was the last mission to carry humans to the lunar surface. And when Gene Cernan climbed back into the lunar module and lifted off from the Taurus Littrow Valley, he left behind a plaque that read, "Here man completed his first explorations of the moon. May the spirit of peace in which we can be reflected in the lives of all mankind." It was a noble sentiment, but it was also, in retrospect, premature because it would be more than half a century before anyone would come close to following in his footsteps. After Apollo, NASA's focus shifted to the Space Shuttle program, a reusable spacecraft designed to make low Earth orbit more accessible and affordable. The shuttle first flew in 1981 and operated until 2011, but it never left low Earth orbit and was designed primarily as a truck for carrying cargo and crew to and from orbital facilities. The International Space Station, which had been continuously occupied since 2000, became the centerpiece of human spaceflight for over 2 decades, but it, too, orbits a mere 250 miles above the Earth, well within the protective embrace of the planet's magnetic field. The grand ambition of Apollo, the idea that humans would push steadily outward into the solar system, visiting the moon and then Mars and then beyond, was quietly shelved in favor of more modest and politically palatable goals. The reasons for this retreat are complex, but they can be distilled into 4 major barriers that have kept humanity trapped in low Earth orbit for more than 50 years. And understanding those barriers is essential to understanding why returning to the moon has been so profoundly difficult. The first barrier is radiation, and it is a problem that most people do not fully appreciate. The Earth is surrounded by a powerful magnetic field generated by the churning of molten iron in its core, and that magnetic field acts as a shield, deflecting the high-energy charged particles that stream through space from the sun and from distant cosmic sources. This magnetic shield creates a region of trapped radiation known as the Van Allen belts, which extend from a few hundred miles above the surface to tens of thousands of miles out, and beyond those belts lies the open ocean of interplanetary space, where radiation levels are significantly higher than anything experienced on Earth's surface or even in low Earth orbit. Astronauts aboard the International Space Station receive a somewhat elevated dose of radiation compared to people on the ground, but they are still largely protected by the Earth's magnetosphere. Astronauts traveling to the moon, however, must pass through the Van Allen belts and then spend days or weeks in deep space, exposed to both galactic cosmic rays, which are high-energy particles originating from supernovae and other violent events elsewhere in the galaxy, and solar particle events, which are bursts of radiation associated with solar flares and coronal mass ejections from the sun. The Apollo astronauts dealt with this problem primarily by minimizing their exposure time. They passed through the Van Allen belts quickly, spending only a few hours in the most intense regions, and their total mission duration was short enough that the cumulative radiation dose remained within acceptable limits. The radiation they absorbed during their flights was roughly equivalent to what a person might receive from a few medical X-rays. Certainly not negligible, but not immediately dangerous. However, the Apollo missions were extraordinarily lucky in one specific respect that is rarely discussed outside of scientific circles. In August 1972, between the Apollo 16 and Apollo 17 missions, the Sun produced one of the most powerful solar particle events ever recorded. If that event had occurred during one of the lunar missions, the astronauts on the surface or in transit would have been exposed to a potentially lethal dose of radiation. The thin walls of the Apollo spacecraft and even thinner walls of the lunar module provided virtually no protection against the kind of high-energy protons that a major solar event produces. Estimates suggest that astronauts caught outside the Earth's magnetosphere during that August 1972 event could have received a radiation dose severe enough to cause acute radiation sickness, and potentially severe enough to be fatal. It was pure chance that no crew was in space at that time. The implications of this near miss are profound. Any future lunar mission must account for the possibility of a major solar event, and that means either providing adequate shielding, which adds enormous weight and cost, or having a plan for a rapid return or shelter, or accepting a level of risk that modern safety standards simply do not allow. For short-duration missions of a week or 2, the radiation risk is manageable but not trivial. For the kind of long-duration lunar surface missions that NASA's Artemis program envisions, with stays of weeks or even months, The cumulative radiation exposure becomes a serious health concern. The moon has no atmosphere and no magnetic field of its own, which means that the lunar surface offers zero natural protection from cosmic rays, solar radiation, or micrometeorites. Any long-term habitat on the moon would need to incorporate heavy radiation shielding, possibly by burying structures under several feet of lunar regolith or by building inside lava tubes, which are natural tunnels formed by ancient volcanic activity that could provide natural overhead protection. NASA has established strict career radiation exposure limits for astronauts, and modeling suggests that a 6-month stay on the lunar surface could approach or exceed those limits, particularly for female astronauts, who are generally more susceptible to radiation-induced cancers. Solving the radiation problem is not impossible, but it requires significant engineering effort and adds substantial cost and complexity to any lunar mission. And it is one of the reasons why simply repeating what Apollo did is not as straightforward as it might seem. The second barrier is cost, and it is arguably the most significant of all the obstacles standing between humanity and a return to the moon. The Apollo program succeeded because the United States government was willing to devote an almost unprecedented share of national resources to a single goal, driven by the existential fear that losing the space race would mean losing the Cold War. That level of political motivation and financial commitment has not existed since. When NASA attempted to return to the moon in the 2000s under the Constellation program, initiated during the administration of George W. Bush, the estimated cost was approximately $130 billion spread over 13 years. And even that staggering sum proved impossible to secure. The Constellation program was ultimately canceled in 2010 under the Obama administration, partly because of budget constraints and partly because of questions about the program's management and technical approach. The fundamental problem is that sending humans to the moon is orders of magnitude more expensive than sending robots, and the scientific return per dollar spent is arguably lower. A robotic lunar rover can be built and launched for a few $100 million, and it can collect samples, take photographs, conduct experiments, and transmit data back to Earth without any need for life support, food, water, air, or a return trip. A human mission, by contrast, requires all those things, plus the enormous additional cost of ensuring that the crew can survive every conceivable emergency and return home safely. The life support systems alone for a crewed lunar mission are staggeringly complex and expensive. Every pound of food, water, and oxygen that an astronaut needs must be launched from Earth at a cost of thousands of dollars per pound. And the spacecraft must be designed with redundant systems for every critical function, because a single failure in a life-critical system 238,000 miles from home could mean death. The argument for sending humans to the moon is not primarily a scientific one. It is an argument about inspiration, about national prestige, about advancing the long-term goal of making humanity a multi-planetary species, and about the unique capabilities that human explorers bring to fieldwork that robots cannot match, including the ability to make real-time decisions, to improvise, to recognize unexpected features, and to respond to changing conditions in ways that even the most advanced autonomous systems cannot. These are valid arguments, but they are difficult to translate into the kind of hard budgetary numbers that congressional appropriations committees demand. When a senator has to choose between funding a moon mission and funding healthcare, infrastructure, education, or defense, the moon mission almost always loses because its benefits are long-term, diffuse, and hard to quantify, while the benefits of domestic spending are immediate, tangible, and politically rewarding. This dynamic has plagued NASA for decades and shows no sign of changing. NASA's budget for fiscal year 2026 is approximately $24.4 billion, which represents about 0.35% of federal spending, a figure that has actually decreased slightly compared to the previous year. Within that budget, the Artemis program must compete with NASA's science missions, its aeronautics research, its Earth observation programs, and its technology development efforts. And the result is that Artemis is chronically underfunded relative to its ambitions. The third barrier is the loss of rocket technology, a phenomenon that might seem paradoxical in an age of rapid technological progress, but is in fact a well-documented reality. The Saturn V rocket that carried Apollo astronauts to the moon was, and in some respects still is, one of the most powerful machines ever constructed. Its first stage was powered by 5 F-1 engines, each producing 1.5 million pounds of thrust, for a combined liftoff thrust of 7.5 million pounds. No rocket engine of comparable power has been built since. When the Apollo program ended, the Saturn V production line was shut down. The specialized tooling was dismantled or repurposed, and the workforce that had designed, built, and tested the rocket dispersed into other jobs and eventually retired. The detailed engineering knowledge required to build a Saturn V, much of which existed not in documents, but in the heads and hands of the technicians and engineers who had done the work, was lost. This is not a metaphor. It is a literal description of what happened. The blueprints for the Saturn V still exist, stored in NASA archives. But blueprints alone are not enough to build a rocket. Modern engineers who have studied the Saturn V documents have noted that they contain gaps, ambiguities, and references to manufacturing processes and materials that are no longer available. Rebuilding a Saturn V from scratch would be almost as difficult as designing a new rocket from the ground up, and in many ways it would be harder, because the new rocket would need to meet modern safety standards that did not exist in the 1960s. NASA recognized this problem when it began developing the Space Launch System, or SLS, its current heavy-lift rocket, which was designed to fill the gap left by the Saturn V. The SLS uses engines derived from the Space Shuttle's main engines and solid rocket boosters derived from the shuttle's solid rocket boosters, repurposing existing technology rather than starting from scratch. The SLS is a capable rocket, but is also extremely expensive and can only be launched once or twice per year due to its throwaway design and the lengthy process required to build each vehicle. Each SLS launch is estimated to cost more than $2 billion, a figure that has drawn sharp criticism from those who argue that commercially developed rockets could do the same job for a fraction of the price. And indeed, the commercial sector has been making rapid progress. SpaceX, the private space company founded by Elon Musk, has been developing Starship, a fully reusable super heavy-lift rocket that, if it achieves its design goals, will be the most powerful and most cost-effective launch vehicle ever built. Starship stands approximately 394 feet tall, making it taller than the Saturn V, and its first-stage booster, called Super Heavy, is powered by 33 Raptor engines that together produce approximately 17 million pounds of thrust at liftoff, more than twice the thrust of the Saturn V. The key innovation of Starship is its full reusability. Both the Super Heavy booster and the upper stage Starship vehicle are designed to return to Earth after each flight, land vertically, and be reflown with minimal refurbishment, much like an airliner that lands, refuels, and takes off again. If this vision is realized, it could reduce the cost of launching cargo and crew to orbit by 1 or 2 orders of magnitude compared to current expendable rockets, fundamentally changing the economics of space exploration. As of July 2026, SpaceX has conducted 12 flight tests of Starship, with a 13th test imminent. The 12th flight, which took place on May 22, 2026, was a landmark event, marking the debut of the Block 3 version of the vehicle and the first launch from Starbay's second launch pad. The flight was largely successful, with the booster performing a controlled descent and the upper stage spacecraft completing an extended orbital flight, though one of the vacuum Raptor engines shut down during ascent, demonstrating both the vehicle's engine-out capability and the continued challenges of operating at the edge of engineering limits. Earlier flights had produced a mix of spectacular successes and equally spectacular failures, including in-flight explosions, loss of vehicle control, and unexpected breakups during re-entry. But each failure provided data that SpaceX used to improve the next iteration. Following the company philosophy of building quickly, testing aggressively, and learning from failure, this approach stands in sharp contrast to NASA's traditional method of exhaustive ground testing and careful qualification before flight. And the tension between these two philosophies is one of the defining dynamics of the current era of space exploration. Starship is not merely a SpaceX vanity project. It is a critical component of NASA's Artemis program, because NASA has selected a modified version of Starship called a Human Landing System, or HLS, as a vehicle that will carry astronauts from lunar orbit to the surface of the Moon for the Artemis 3 mission. This means that NASA's ability to land humans on the Moon is directly dependent on SpaceX's ability to mature Starship into a safe, reliable, human-rated vehicle. And that dependency introduces a significant element of schedule risk into the Artemis program. The fourth barrier is the overall challenge of ensuring crew safety, which encompasses everything from the design of the lunar landing vehicle to the life support systems that will keep astronauts alive on the surface, to cultural and institutional pressures that demand a level of risk management far more stringent than what was accepted during the Apollo era. No one has attempted a crewed lunar landing since 1972, and even uncrewed soft landings on the Moon have proven remarkably difficult in recent years. In June 2025, the American-based company Space, operating on behalf of a private Japanese venture, attempted an uncrewed soft landing on the Moon with its Resilience lander and failed, the vehicle crashing into the lunar surface due to errors in its laser range-finding system. Other recent commercial attempts have met similar fates. Astrobotic's Peregrine lander suffered a propulsion failure in early 2024 and never reached the Moon. Intuitive Machines managed 2 lunar landings with its Nova-C lander, but both vehicles tipped over upon touchdown, limiting their operational capability. These failures underscore a sobering truth. Landing on the Moon is genuinely hard, and doing it safely with humans aboard is exponentially harder. The lunar surface presents a hostile environment unlike anything on Earth. There is no atmosphere to slow a descending spacecraft, so the entire deceleration from orbital velocity to a gentle touchdown must be accomplished with rocket engines, requiring precise throttle control and accurate navigation down to the final seconds. The surface itself is covered with regolith, a fine, abrasive, electrostatically charged dust that clings to everything it touches. Apollo astronauts found that regolith got into the seals of their spacesuits, degraded the visors of their helmets, and was so pervasive that it was impossible to keep it out of the lunar module cabin. Some astronauts reported irritation in their eyes and lungs after removing their helmets inside the spacecraft. And subsequent analysis has shown that lunar regolith particles are sharp-edged and potentially toxic when inhaled, because they have never been weathered by wind or water. For short Apollo-style visits of a few days, regolith was a nuisance. For the multi-week or multi-month stays that Artemis envisions, it could be a genuine health hazard, requiring advanced dust mitigation systems that do not yet exist. The thermal environment on the Moon is equally extreme. During the lunar day, which lasts about 14 Earth days, surface temperatures can exceed 250 degrees Fahrenheit in direct sunlight. During the equally long lunar night, temperatures plunge to nearly 300 degrees below 0 Fahrenheit. Any habitat or spacesuit must be capable of managing these wild temperature swings. And any equipment left on the surface must be able to survive the deep cold of the lunar night without cracking, freezing, or otherwise failing. Power is another critical concern. Solar panels work well during the lunar day, but are useless during the 2-week night, which means that any long-duration mission needs either massive battery banks, a nuclear power source, or a location near one of the lunar poles where certain elevated areas receive near-continuous sunlight, so-called peaks of eternal light. NASA's current planning for Artemis surface missions focuses on the lunar South Pole precisely because of the favorable lighting conditions there, as well as the presence of water ice in permanently shadowed craters, which could potentially be extracted and used for drinking water, oxygen production, and even rocket fuel. But the South Polar region also presents its own challenges, including rugged terrain, deep shadows, and communication difficulties due to the low angle of the sun and the horizon. The cultural shift in risk tolerance since the Apollo era cannot be overstated as a factor in why returning to the moon has taken so long. During Apollo, NASA operated under a wartime mentality. The space race was understood as a battle, and in battle, casualties are tragic but expected. When the Apollo 1 fire killed 3 astronauts, the program paused, redesigned the spacecraft, and pushed forward. The implicit understanding was that some astronauts might die in pursuit of the moon, and while every effort will be made to prevent that, the program would not be stopped by the possibility. That attitude is no longer tenable. The Space Shuttle program demonstrated the consequences of pushing too hard against safety margins. The Challenger disaster of 1986, in which 7 crew members died when a faulty solid rocket booster seal failed during launch, and the Columbia disaster of 2003, in which 7 more crew members died when damaged heat shield tiles led to the breakup of the orbiter during re-entry, fundamentally changed NASA's culture. After Columbia, NASA adopted a much more conservative approach to risk, with extensive review processes, safety boards, and independent oversight mechanisms designed to prevent the kind of schedule-driven decision-making that had contributed to both disasters. This is, without question, a good thing. Human lives should not be sacrificed for schedule or prestige, but it has also made the process of developing and certifying new crewed spacecraft enormously slower and more expensive, where Apollo moved from President Kennedy's speech to a moon landing in just 8 years. The Artemis program has been in various stages of development for nearly 2 decades and has not yet landed anyone on the moon. The Orion spacecraft that will carry Artemis crews was first funded in 2006, and the SLS rocket that will launch it was authorized in 2010. 16 years of development preceded the first uncrewed test flight of the combined system in November 2022, and the first crewed flight did not occur until April 2026. By Apollo-era standards, this pace would have been considered unacceptably slow. By modern standards, it is considered appropriately cautious. The conspiracy theories that surround the Apollo moon landings deserve to be addressed directly, not because they have any scientific merit, but because they are widely believed and because they muddy the public conversation about why we haven't returned. The most common claims are familiar to anyone who has spent time reading about space on the internet. Conspiracy theorists point to apparent anomalies in the photographs and video footage from the moon, such as shadows that appear to point in different directions, which they claim is evidence of multiple studio lights rather than a single sun, or the American flag that appears to ripple as if blown by wind, which they claim is impossible in the vacuum of the moon. These claims have been thoroughly and repeatedly debunked by scientists, photographers, and lighting experts. The shadow anomalies are easily explained by the perspective effects of wide-angle lenses combined with uneven terrain. When parallel rays of sunlight fall on a bumpy surface, the shadows they cast can appear to diverge or converge depending on the viewing angle, and wide-angle lenses exaggerate this effect. If multiple artificial lights have been used, objects would cast multiple shadows, but in every Apollo photograph, each object casts exactly one shadow, consistent with illumination by a single light source, the sun. The flag appeared to wave not because of wind, but because it was equipped with a horizontal, telescoping rod along the top edge to hold it extended, when astronauts planted the flagpole by twisting it into the lunar soil. The rotational motion caused the flag to swing back and forth, and because there is no air resistance on the moon to dampen the oscillation, the flag continued to move for a noticeably long time after being disturbed, giving it the appearance of fluttering. Once left alone, however, the flag became perfectly still, as any video footage clearly shows. The claim that the Van Allen radiation belts would have killed any astronaut attempting to pass through them is equally unfounded. The Apollo spacecraft traversed the belts in a matter of hours, and the trajectory was carefully chosen to minimize passage through the most intense regions. The total radiation dose received by Apollo astronauts during belt transit was measured and found to be roughly equivalent to that of a few chest X-rays, well within safe limits. The Van Allen belts are a genuine hazard for spacecraft that linger in them, or for astronauts who would need to perform extravehicular activity while passing through them, but a quick transit in a metal spacecraft poses no significant health risk. Every other conspiracy claim, from the alleged absence of stars in the photographs, which is simply the result of exposure settings optimized for the brightly lit lunar surface, to the question of who operated the camera that filmed Armstrong descending the ladder, which was a remotely operated television camera mounted on the outside of the lunar module, has been explained in exhaustive detail by experts in the relevant fields. The physical evidence of the Apollo landings is overwhelming and includes hundreds of pounds of lunar rock and soil samples brought back to Earth, retroreflector arrays placed on the lunar surface that scientists still use today to bounce laser beams off the moon and precisely measure its distance from Earth, thousands of photographs and hours of video footage, and the independent tracking of Apollo missions by observatories around the world, including facilities in countries that had no reason to participate in an American deception. The moon landings happened. They are among the most thoroughly documented events in human history. The conspiracy theories persist not because of any genuine evidence, but because of a deep-seated distrust of government institutions, a misunderstanding of physics and photography, and the psychologically satisfying simplicity of a narrative in which a powerful entity is hiding a grand secret. But indulging these theories is not only wrong, it is actively harmful, because it distracts from the genuinely important and fascinating question of why we stop going and what it will take to start again. The answer to that question is now taking shape in the form of NASA's Artemis program, the most ambitious human spaceflight initiative since Apollo itself. Artemis, named after the twin sister of Apollo in Greek mythology and the goddess of the moon, aims to return American astronauts to the lunar surface and eventually establish a sustained human presence there, using the moon as a proving ground for the technologies and techniques that will eventually be needed for crewed missions to Mars. The program's roadmap has evolved significantly since its inception and has been subject to repeated delays. But as of mid-2026, it has achieved its first major milestones and appears to be on trajectory, however slow, toward an actual lunar landing. Artemis I, the first mission in the program, launched on November 16, 2022, sending an uncrewed Orion spacecraft on a 25-day journey around the moon and back. The mission was largely successful, demonstrating the performance of the SLS rocket and the Orion spacecraft's ability to survive the rigors of deep space and re-entry, though engineers noted that the heat shield exhibited unexpected patterns of material loss during re-entry, a finding that required extensive investigation and contributed to delays in subsequent missions. Artemis II, the program's first crewed mission, launched on April 1, 2026, carrying 4 astronauts: Commander Reed Wiseman, pilot Victor Glover, and mission specialist Christina Koch and Jeremy Hansen, the last of whom is a Canadian Space Agency astronaut and the first non-American to travel to the moon. Glover became the first person of color, and Koch the first woman to fly to the moon. The mission followed a free return trajectory, looping around the moon at a closest approach of approximately 6,400 miles before it turned to Earth for a successful splashdown in the Pacific Ocean on April 10, 2026, after a mission duration of approximately 9 days. The flight covered over 700,000 miles and reached a peak velocity of nearly 25,000 miles per hour. The mission was hailed as a triumphant success, validating the Orion spacecraft's life support systems, navigation, and thermal protection with a human crew aboard, and setting the stage for the next and most critical step, an actual landing. That landing is planned for Artemis III, which is currently scheduled for no earlier than 2028, though the exact date remains uncertain, and dependent on the readiness of the Starship human landing system. The mission profile for Artemis 3 envisions 4 astronauts launching aboard an SLS rocket in an Orion spacecraft, rendezvousing in lunar orbit with a pre-positioned Starship lander, and then 2 of the astronauts transferring to the Starship and descending to the surface near the lunar South Pole while the other 2 remain in orbit. The surface crew would spend approximately a week on the Moon, conducting science experiments, collecting samples, and testing equipment before ascending back to lunar orbit, reuniting with their crewmates in Orion, and returning to Earth. If it succeeds, Artemis 3 will be the first time humans have walked on the Moon since December 1972, and the first time a woman and a person of color have set foot on the lunar surface. But achieving that goal requires the Starship HLS to be fully developed, tested, and certified for crewed operations, and as of July 2026, that process is still underway. SpaceX must demonstrate that Starship can reliably reach orbit, be refueled in space through a series of tanker flights, travel to lunar orbit, descend to the surface, land safely, and then ascend back to orbit, all without failure. No uncrewed lunar landing demonstration has yet been attempted, and that demonstration must succeed before any crew sets foot in the vehicle. NASA's own internal assessments have identified the Starship HLS development schedule as the single greatest risk factor for Artemis 3. And while SpaceX has made impressive progress with its rapid iteration testing approach, the gap between a successful orbital test flight and a safe crewed lunar landing is substantial. Beyond Artemis 3, NASA has outlined an ambitious series of follow-on missions designed to build toward a permanent human presence on the Moon. Artemis 4 and subsequent missions will begin construction of the Lunar Gateway, a small space station that will orbit the Moon and serve as a staging point for lunar surface missions. The Gateway is being built through international collaboration, with modules contributed by the European Space Agency, the Japan Aerospace Exploration Agency, and the Canadian Space Agency, among others. It will provide a habitat for astronauts in transit to and from the surface, a platform for scientific research, and a communications relay for surface operations. In the longer term, NASA envisions the construction of a surface-based camp near the lunar South Pole, where astronauts could stay for weeks or months at a time, supported by pressurized rovers that would allow them to travel significant distances from the base without wearing spacesuits. A particularly notable element of this vision involves a pressurized rover being developed through a partnership with Japan, which would allow astronauts to live and work inside the vehicle in a shirt-sleeve environment, greatly extending the range and duration of surface exploration. This rover is expected to be deployed on Artemis 7 or later, possibly in the early 2030s. Japan has also secured an agreement, formalized in an April 2024 accord between the two governments, to have 2 of its own astronauts walk on the Moon as part of the Artemis program, making it the first country other than the United States to land its citizens on the lunar surface. 2 Japanese astronaut candidates were formally certified in October 2024 and are currently in training for potential assignment to future Artemis surface missions. The question of whether all of this will actually happen on the timelines that have been announced is a legitimate one, because the history of post-Apollo lunar ambitions is littered with canceled programs, broken promises, and optimistic schedules that bore no resemblance to reality. Every American president since George H.W. Bush has, at some point during their term, announced a plan to return to the Moon, and every one of those plans has either been canceled by the next administration or delayed to the point of irrelevance. The current political landscape adds another layer of uncertainty. The budget environment in Washington is tight, with competing demands from defense, entitlement programs, infrastructure, and debt service leaving relatively little room for discretionary spending increases. NASA's fiscal year 2026 budget of $24.4 billion represents a slight cut from the previous year, and while the Artemis program continues to receive funding, it is not receiving the kind of dramatic budget increases that would be needed to accelerate the schedule. The current administration has signaled continued support for human space exploration, but has also emphasized fiscal efficiency and cost discipline, which in practice means that Artemis will proceed at a sustainable but not aggressive pace. International collaboration helps to spread the financial burden and adds political resilience to the program, since canceling Artemis would now mean breaking commitments not just to American taxpayers, but to partner nations that have invested their own resources in effort. But international partnerships also add complexity, because each partner's contributions must be coordinated, and delays in one partner's hardware can cascade to the entire program timeline. Despite all these challenges, there are genuine reasons for optimism that the current era will finally see humans return to the moon. The most important is the emergence of the commercial space industry as a major force in human spaceflight. SpaceX has already revolutionized the launch industry with its Falcon 9 rocket, which has flown hundreds of missions and demonstrated routine reusability of its first-stage booster, dramatically reducing launch costs and increasing launch cadence. If Starship achieves even a fraction of its promised cost and performance targets, it will make missions to the moon and beyond far more economically feasible than they have ever been. Blue Origin, the space company founded by Jeff Bezos, is developing its own heavy-lift rocket, New Glenn, and has been selected by NASA to develop a second lunar lander for Artemis missions beyond the initial Starship HLS, providing redundancy and competition in the lander supply chain. Other companies are developing lunar cargo delivery services, lunar surface power systems, communications networks, and resource extraction technologies, creating an emerging commercial ecosystem around the moon that did not exist during the Apollo era. The Artemis Accords, a framework of principles governing the responsible exploration of the moon that has been signed by dozens of nations, provides a diplomatic foundation for international cooperation and resource sharing on the lunar surface. And the scientific case for returning to the moon has only grown stronger in the decades since Apollo, as new data from orbital missions and robotic landers has revealed the presence of water ice at the lunar poles, confirmed the existence of lava tubes that could serve as natural shelters, and raised new questions about the moon's geological history and its potential as a platform for astronomy, material science, and biological research. The path back to the moon is not a straight line. It is a winding, fitful, frustrating journey that has already consumed decades and billions of dollars, and it will consume many more of both before it reaches its destination. The barriers are real: radiation that threatens crew health, costs that strain national budgets, rocket technologies that had to be rebuilt almost from scratch after a half-century gap, and safety requirements that rightly demand levels of testing and verification that the Apollo era never contemplated. But none of these barriers is insurmountable. Each one is a solvable engineering, financial, or political problem, and the tools and talent needed to solve them exist today in ways they did not even a decade ago. The question is not whether humanity can return to the moon. We can, and we almost certainly will. The question is whether we will do so with the sustained commitment, the adequate funding, the international cooperation, and the patient determination that the task requires, or whether we will repeat the pattern of the past half-century, announcing grand plans, achieving partial progress, and then losing focus before the job is done. Artemis 2 has already proven that humans can once again travel to the vicinity of the moon and return safely. The Starship program, despite its setbacks and delays, is making measurable progress toward a goal of affordable, reusable super heavy lift capability. The international partnerships that undergird the Artemis program are broader and more deeply committed than anything that existed during Apollo. And the commercial space industry is providing a competitive, innovative, cost-conscious complement to government-led exploration that has no precedent in the history of spaceflight, the most realistic projection, accounting for the inevitable delays and setbacks that accompany any program of this complexity, is that humans will walk on the moon again sometime around 2028 to 2030, and that by the mid-2030s, the first elements of a permanent lunar outpost will be in place. From that outpost, astronauts will conduct science that cannot be done from orbit or by robots, test the technologies needed for eventual crewed missions to Mars, and begin the long process of learning how to live and work on another world. The 50-plus years that humanity spent confined to low Earth orbit will, in retrospect, look less like a failure and more like a necessary period of consolidation, during which we learned to build space stations, to cooperate internationally in space, to develop robotic exploration capabilities of extraordinary sophistication, and to nurture a private space industry capable of driving down costs and accelerating innovation. All of those capabilities are now being brought to bear on the challenge of returning to the moon. And while the road ahead is long and uncertain, the destination is, for the first time in decades, genuinely within reach. The next human footprint on the lunar surface will not be a one-time stunt performed for political points, as Apollo arguably was, but the beginning of a permanent expansion of human civilization beyond the planet of its birth. A first step not just to the moon, but onward to Mars, to the asteroids, and eventually to destinations that we cannot yet imagine. That is the promise of the current moment in space exploration, and it is a promise worth the patience, the investment, and the risk that fulfilling it demands.